like honestly,
first
it's
one.
fun.
Yeah, and I was, so I was sitting there, I was like,
Good morning, everyone.
Second time I did it. First time mom. Stop. Yeah, so we can take it out.
All right. How's everyone feeling? Valid. So, probably the main thing on the agenda is test 2 will begin this afternoon. You'll take it one of the 3 afternoons between today, Tuesday, and Wednesday. And lecture today is going to be focused primarily on making sure everyone feels comfortable for that. So, it's review day. With that said, my goals would be to look over the study list, look over the practice questions, look over old homeworks, anything that you guys need to discuss or have on your mind before you take the test. So, what's on your minds? Practice test number 7.
And number 11B.
7 and 11B.
Can we just do all of 11?
Yes, yes we can. Make it a list.
And you also can go over the concepts of 14 and 16.
Can do. The projector decides to play nice. All right, number 7. We've got the International Space Station orbiting the Earth. The space station has a mass of 400,000 kilograms, which is a lot of metal. And it is orbiting at an orbital radius of 6,600 kilometers from Earth's center. Separately, the mass of Earth is listed at 6.0 times 10 to the 24th kilograms, and we've been asked to calculate a few things. First up, what is the force of gravity between the Earth and the space station? Now, on planet Earth, we tend to use mg 10 times 10 to find weight, but since the station is not on Earth's surface, we have to use universal law of gravitation, which is a big G times m1 times m2 over r squared. Big G is located on the formula sheet with the formula itself. That is 6.67 times 10 to the negative 11th. Next is the mass of the 2 items. First, we've got the mass of the station in kilograms, then we've got the mass of the Earth in kilograms, and then divided by radius squared. Now, we like meters instead of kilometers, so I plugged in 6,600,000 meters, and then that number needs to be squared. Overall, I realized that me putting commas in the wrong place probably made that a little hard to read, so I will rewrite my answer. It should be 3,674,931.1 newtons is the force of gravity between the Earth and the space station, which is a lot. It is not weightless. If you didn't quite get that answer, doesn't necessarily mean you set anything up wrong, but it could mean that your calculator didn't interpret what you were telling it correctly. Calculators often, I find, have trouble with this one, not only because there's a bunch of really big and really small numbers that have a lot of times 10 to those that you have to input correctly, but especially you have to input the r squared on the bottom correctly. The way that I would, first of all, I wouldn't recommend doing this all on one line anyway. But if you did want to type it all in on one line, I would do it something like this. 6.67 e negative 11. And I want to make it clear, this e, it's not the natural logarithm e, it's the times 10 to the power of e that your calculator uses. In fact, your calculator probably uses a very blocky looking e for it, so let me write it like that instead. Next is 400,000, which you could also write as 4 times 10 to the 5th if you wanted. Then the mass of the Earth, 6.0 times 10 to the 24. Then I've got all the, I usually keep all of those within parentheses to make sure that all of the times 10 to this are applied to the correct things. And then after the last closed parentheses, divided by, open one more parentheses, then input the 6,600,000, and make sure only that is being squared. Does that help anyone who was having trouble with the first part?
So whenever we use this formula, we need to use meters.
Yes. Meters is our preferred metric unit. And most formulas and constants are designed in this class to use meters. Part A feel okay? All right. Part B asks, what will the centripetal force between the Earth and the station be? And the answer to that is the same as the force of gravity. The force of gravity is going to be acting as the centripetal force that causes the station to move in a circle around the planet. And basically that just means that wherever you'd see Fc, you can now plug in the value you just found for Fg. And therefore in part C, how fast must the station be moving to maintain its orbit, you can use the centripetal force formula, plug in the value for gravity you just found, plug in the mass of the moon, not the moon, wow, getting my examples mixed up. Plug in the mass of the space station, because the space station is the thing doing the orbiting. The centripetal force formula is about the orbiting object, therefore it's the mass of the station that gets reused here, not the mass of the Earth. Then same orbital radius and solve for V, and the space station is booking it at approximately Mach 20, about 20 times the speed of sound, I think. It's a good thing there's no air up there. We'd be making sonic booms literally every second of every day. Thank you. How's that feel for number 7? Any issues before moving on? All right. Next one on the agenda is 11. Teeter-totter. So this one is, if you remember the seesaw lab that we did, this is, in my opinion, very similar to that very last question on the end of it, where I gave a hypothetical seesaw with a bunch of masses hanging from it, and where the fulcrum was not under the center of mass of the object itself. To kind of look at the picture real quick, we have a 4 meter long, seesaw. The center of mass of that seesaw is going to be dead center, but the fulcrum is not under the center. The fulcrum is half a meter to the left of the center. And since that center of mass is not being supported, the weight of the meter stick, weight of the seesaw, is now generating torque. We have to factor that into our calculations. For that reason, there will be 3 torques that need to cancel out. But before that, the first question says, what is the net torque on this balanced seesaw? If it is balanced, by definition, the net torque has to be 0 Newton meters. Kind of the same way as a normal stationary object, like any of the things on my desk. If they are currently stationary, they are currently in equilibrium, therefore the net force on them equals 0. If this isn't rotating, it is in equilibrium and the net torque on it must be 0. So that's automatically the answer to part A if it is a balanced seesaw. Does that sound all right? Okay. If it is balanced, that means that all of the torques here have to add up to 0. So net torque, we're going to add up the 3 torques that are acting on this thing, and they must all add up to 0. So to identify the 3 torques that are present, we've got the weight of this 120 kilogram object, which is currently at 1.5 meters away from the fulcrum. So for torque 1, I've got a radius of negative 1.5. We'll talk about the negative in a second. Note again, torque is radius times force. So first here I've got the radius between this mass and the fulcrum, and then I've got the weight of that mass. Since this is on planet Earth, we can use 10 for G, and so for weight, I'm just plugging in the mass of 120 kilograms times 10. I'm just using the times 10 to be thorough, technically, because what we want here is the force of gravity, not necessarily the mass. And that is the first torque. The second torque that I have listed here is the torque caused by the mass of the seesaw itself. Note again, fulcrum is not under the center of mass, therefore the mass of the meter stick, I keep saying meter stick because I'm so used to that lab. The mass of the seesaw is generating torque, bless you. In this case, for torque 2, the radius is 0.5, bless you. We don't know the mass of the seesaw, that's ultimately what we're going to be finding here, but whatever that mass is, its weight is what is generating torque here, so I have left in m times 10 for the weight of the physical log of the seesaw. And then torque 3, we've got 40 kilograms spaced 2.5 meters away from the fulcrum. So for torque 3, we've got a radius of 2.5, a mass of 40, and 10 again for the strength of gravity. And that's all the torques identified. They must all add up to 0, and since m, the mass of the physical seesaw, is the only unknown, we are good to solve for it. In order to get there, though, I want to point at, question?
Okay, you said 40 and not 4.0 because we convert into, or is that 4.0?
That is 40. That's 40 kilograms.
Okay, I see it now. You do.
All right. Yeah, those are both meant to be 40s is my intent. And since we know all 3 of these, we can find this number, we can find this number, and we just solve for the m in there. But a small technicality to make this work correctly, I did make the radius in torque 1 negative. And that's because this object is on the opposite side of the fulcrum as the other 2. Therefore, the torques they're generating work against one another. These 2 torques are trying to make it spin clockwise, whereas this torque is trying to make it spin counterclockwise. They're working against one another, and we have to represent that somehow. I am choosing to represent that as making R1 negative to indicate it is basically on the opposite side of the origin. If you think of the fulcrum as the origin, 0, 0, then this point would be negative 1.5, 0. So that is why I put a negative sign there. You do have to acknowledge that somehow. There's a couple different ways you could, but this is my preferred option. And I did kind of skip my work. I do kind of do that when I'm making the keys, unfortunately. So I'll try to show the next couple lines of math. Keep misplacing my calculator. -1.5 first number becomes negative 1,800. Then 0.5 times 10 is just going to be 5m. And 2.5 times 40 times 10 is 1,000. Any issues with setting it up to this point? All right. Send negative 1,800 and also positive 1,000 over to the other side. That's going to give us 1,800 minus 1,000 equals 5m. Therefore, 800 equals 5m. 800 over 5 equals m, which hopefully is 160 kilograms. How's this one feel? Any questions, concerns, etc. before looking at another one? All right. Next up, we've been asked about 14. All right, so this is a concept question. I kind of combined Pascal's principle and gas law into one question here for the sake of the review. You exert forces on various contained fluids. Keep in mind, fluid can mean liquid or gas. And so the way that the question follows from here is, how do each of those two separate types of thing behave when acting under pressure? The first question is, will a liquid compress to a smaller volume when you exert pressure on it? It won't. Liquids are considered non-compressible. We consider them to have non-definite shape, but yes, definite volume. A liquid, generally speaking, does not get any smaller when you compress it. And that is why you can create systems like we talked about with the liquid reservoir that you can use to elevate a car. If you exert pressure on one side of the liquid doesn't get any smaller. Instead, it just flows to the other side and starts pushing up on the car. So that only works because the liquid isn't compressible. Now, conversely, a gas will compress when pressurized, and that is how you can squeeze several warehouses worth of helium into a single tank that you can buy at a party store. So gases do compress when pressurized. That is one of the main differences between liquids and gases. Gases do have definite volume. I said that backwards. Liquids have definite volume, gases don't. Does that sound okay first? All right. Now, following up from that, what happens to the pressure within a confined liquid if you increase the pressure you are exerting on it? If you exert pressure on one part of this liquid system, the whole liquid system pressurizes based on it. You will increase the pressure across the whole system. Since the liquid can't get any smaller, it just has to flow and carry that pressure with it to the other side, basically. You could hypothetically exhibit this with a water balloon, because if you tried to squeeze a water balloon, you'd pressurize the whole thing and it would squeeze out of your fingers because of the higher pressure. This is again different to C, which is asking about gases again. What happens to the volume of a gas if you quadruple the pressure acting on it without changing the temperature? There's a specific formula for gas law, which, is that one on here? No, that's another tweak we need to make. Gas law says that pressure 1 times volume 1 equals pressure 2 times volume 2. Basically, if you increase one of these, the other will decrease by a proportional amount. Let's say that you start with 1 atmosphere of pressure acting on 1 liter of gas, and you, what did I say, quadruple the pressure. In order for the two sides to remain equal, V2 is going to have to shrink to 1/4 so that both sides still equal 1. quadruple the pressure, you are physically squeezing the gas 4 times as much. It will shrink to four times smaller size, 1/4 the size. So if you take a warehouse full of helium and you want to squeeze it into a cylinder, 100 times smaller, you have to create 100 times the pressure acting on it to get it into that tank and keep it in there. So those tanks are highly pressurized and you need to be careful with them, whether it's helium or propane. How's that sound? All right. Now, again, I wrote this after writing the test. This is a similar way that these concepts would come up to the test itself. So this is, I want you to know about this knowledge, but this is the extent to which you have to use it. Does that sound all right? All right. And we've also been asked about 16. A submarine sonar system emits a sound pulse which travels outwards, echoes off of a whale, and comes back after a total of 20 seconds. The speed of sound in water is 1,500 meters per second. How far away from the submarine is the whale? My intent with this one was just to use the old-fashioned velocity formula, because since waves have velocity, they do travel a distance per unit time. And you just want to know the distance the sound wave travels in a certain amount of time. The main complication here is when you're using an echo for this sort of thing, that 20 seconds is the time it took for the wave to travel from the sub, hit the whale, and then go back. So technically, the sound travels double that distance in that amount of time. It goes there and goes back. It runs the football field and then doubles back around, covering 200 yards. So there's really 2 ways you could think about it. You could plug in the 20 seconds, get the double length, and cut that in half. What I chose to do instead was just note it would have taken the sound in 10 seconds out and 10 seconds back. So I just plugged in 10 seconds for the time and got 15,000 meters. Does that make sense? This is what whales spend all day doing, just echolocating, trying to find their friends. And krill, friends and krill. How you guys feeling?
So like number 1, there's gonna be examples, not so much definitions, right?
You're right. On the practice test, I'll usually ask you to define something so that you write it out at least once in your own hand, you check the definition, you write it down. On the actual test, I would ask, we'll say, for example, pressure. Rather than asking you to write out what pressure is, I would probably give you a situation like in, I'm putting 2 pressure at depth questions on here. I would probably ask a situation where you know, like say force and area, pressure and area, and I ask you for force, kind of demonstrating that you understand pressure is force over area. In another scenario, yeah, for the concept questions on the actual test, I try to make them very short, preferably 1-word answers, like, is there a measurable centrifugal force acting on this object? Yes, no, maybe. And the answer would be no, because centrifugal force doesn't exist. That sort of thing. Does that answer the question? Yeah, when I write the test, my goal is to try to make it expedient, because you're in here doing a lot of questions in a relatively short amount of time. I don't want you having to write your thoughts out being the thing that takes you the longest. So yeah, this is always meant to take you a little bit longer so that you get the practice in and make your mistakes on it. Plus, you can always look up the answers. You don't have to write it, I guess. I'm just rambling at this point. Does that answer the question? Okay.
Same thing with like number 4, is gonna be example, or is gonna be.
Yes. Well, yeah. 4 in this case, I gave you the words, and you kind of just have to match them. So in this case, I'd be expecting 2-word answers, but using words that I give you, and you just have to know which ones go where. And my goal is expedience. This is a good example. Thank you. Anything else on your minds? Yes.
On the formula sheet, for the formula for period, it says like 1 over frequency.
Correct.
Is that 1 like definite, or that changes, right?
No, that's definite.
That's definite?
If you know frequency, 1 over frequency is period. That is definite, guaranteed.
Okay.
That is just the mathematical process of inverting a number. You divide 1 by that number, and that is the number flipped upside down, along with its unit. And frankly, you could write it the other way too. Frequency is also the inverse of period. So you could also write F equals 1 over T. And it is 1. It is very specifically the number 1. Does that answer the question?
Yeah, so then for 10, like, so it would be 1 over, I guess, 1, but I don't know. Can you do number 10?
Yes, absolutely. We have a spring oscillating up and down. It completes 1 oscillation every 5 seconds. And I listed amplitude kind of as a red herring. You didn't end up needing it. The first question is, what is the period of oscillation? The definition of period is time per oscillation. So it takes 5 seconds per, sorry, 0.5 seconds, my mistake. 0.5 seconds per oscillation. Therefore, the period is 0.5 seconds. That is the time for 1 single event. Then the second question is, what is frequency? You could start from either or of these two. They mean the same thing. But I chose to rearrange it as F equals 1 over T. So you take that period of oscillation, the 0.5 seconds, and it goes underneath here. So you have a 1 over 0.5. Yes?
So do we have like 2 formulas for period? Because I thought period is 1 divided by.
Yes, yes we do.
Point?
So we have two formulas for it.
There, yes, I apologize. I'm just now realizing I only put one of them on the formula sheet. So if I was to list them both out, and please absolutely write these on your sheet since I forgot to include them myself. Period is 1 over frequency. That is true, that absolutely works. Separately from that, the definition of period of oscillation is time over number of events. Okay, I'm glad. I'm sorry for the confusion.
It's okay.
And you know what, I'll even list out the 2 different ways to write frequency as well, if you want them. Frequency is likewise 1 over period. Just, these are the same formula, just rearranged. And technically then, I can rearrange this to also say, frequency is number of events over time. So if you wanted to think about this in a slightly different way, answering the frequency question, we've got 1 event over 0.5 seconds. So 1 over 0.5, 2 hertz. that wasn't really a formula, I'll admit. Most boats try to have 40% of their total volume under the water. What would that make your boat's total volume? This 0.5 from the first part is the amount of the boat that is under the water. Which the question is implying is only 40% of the total boat. So the overall volume of the boat must be greater than that if only 40% of it is 0.5. And what I did was I took volume total times 40%, and 40% of the total would be 0.5. So admittedly less of a formula, I fully admit. But, okay, yeah, in the interest of full disclosure, I don't ask you to do something like that on the actual test. I mainly just wanted you to remember that the volume in the formula is just the submerged part of the object. But again, I don't want to trick people, so full disclosure, I technically don't ask you to do this on the test. Does that sound all right? All right. Now, again, just to explain what I did do, 40% of the total is 0.5, and you can just multiply the percent by the total to get that. So what I then did was I just divided by 40%, and technically to do that, I just wrote 0.4 rather than the percent version. So 0.5 over 0.4 gives 1.25 meters cubed. And if you then take 40% of 1.25, you get 0.5. So this would be the total volume of the boat, and this is just the 40% chunk of it that is under the water. And I only did any of this on the practice test to make sure that you guys just know for the future that only the submerged portion of the object creates any buoyant force. The water doesn't know about the other 60%, therefore the other 60% doesn't make any buoyant force, it's just weight. Most boats do something like this. They have to keep enough hull underwater to generate the needed amount of buoyant force for the whole boat. Does that answer any relevant questions? Okay. I'm glad you asked. Anything else on your minds? All right. Well, it is review week, so you are welcome to hang around, study, rest your brain, or wait until you have questions. At this point, it's 11:07. So, again, welcome to sit around in case you think of another question. But if you feel satisfied with the amount of review for right now, you are welcome to head on out of here, get some rest, review as you will, and if I don't see you later today, please have a wonderful day. And please let me know if you have any questions, needs, concerns, etc. while studying. I'll be either here or in my office.
Oh, you want one?
See that read?
squared is in the numerator of that fraction. So to get it by itself, I would divide both sides by 400,000 and then multiply both sides by technically 6,600,000 and then take the square root, which, you know, I can do all that on the board.
I think that was my problem that I was.
Oh, read my lab.
Oh, thank you.